Welcome to the second example in the chapter of strain. The question reads, a gap of 0.18 millimeters exists between the rigid plate and bar B before load P is applied to the system, as shown in the figure below. After load P is applied, the axial strain in rod B is negative 2,500 micrometers per meter. Determine the axial strain in rod A. Okay, so immediately we are given that the gap between rods B and C is 0.18 millimeters. So this gap right here is 0.18 millimeters. So that's our first given. We're going to say gap, or actually let's give it a variable. Let's call it delta. So this delta is equal to 0.18 millimeters. Okay. What else are we given? We're given that it's kind of a no and some information. So when load P is applied, the axial strain in rod B is negative 2,500 micrometers per meter. We want to convert this into meters per meters. It's still unitless, but we want to convert it. So negative 2, and how you do that is just multiply by 10 to the negative 6. You end up with meters per meter. Okay, what does this mean, like physically, like on the diagram, for example? Well, this basically means that once we apply this load, the only logical reasoning is why, okay, even if load P is applied, why do they're not even touching this point. Why is bar B affected? Why does it have a strain? Well, this is because this implies that once we applied load P, it's gonna push this rigid bar C. That is very important. That's actually, I'm gonna write it before I even continue the explanation. It's a rigid bar C, right? Once I applied this load, what does rigid mean again? It won't bend like this, right? We're going to get into bending very soon. Or actually not very soon, but eventually, it's going to be completely straight. So this bar C is going to be completely straight. So it's going to start up here, for example. And then once I applied this load C, it's going to sink down into bar B, right? Therefore causing a strain, right? So it's going to go past this delta 0.8, or what do we call it? It's going to go past this delta. It's going to go past 0.18 and further into bar B, causing it to strain. Okay? What we want to find now is how much this bar, after we apply this load, how far it went, right? Okay. Well, how far it went is basically the gap, right? We said the gap is 0.18. Remember, we gave it a variable, so 0.18, plus the change in length of bar B, right? That's how far this rigid bar C has traveled down, correct? So as a summary, once we apply this load to bar C, this rigid bar is not going to bend. It's going to sink down, and it's a huge exaggeration, but it's going to sink down into bar B, right? And spoiler alert, but it's also bringing bar A, which is the point of interest, with it. But we'll get to that in just a second, right? So, summary again, I really want this to be understood because it's very important for later on. Basically, the change in length, or the displacement of bar C is equal to the gap plus the change in length of bar B. How do I find the gap? It's given to us. How do I find the change in length of bar B? Well, now we can go back to our strain equation. What's strain equal to? Strain is equal to the change in length of bar B divided by the original length of bar B. How do I find this? I have the original length of bar B. I have the strain. I basically, if I isolate for change in length of bar B, I will get the strain of B times the original length of bar B is equal to the change in length of bar B. Therefore, if you multiply these two numbers together, this one and the length, so 2, you're going to get negative 0.005 meters. Okay? Okay, we can go back to analyzing the diagram again. So what does this mean? Remember, delta L B is equal to negative 0.005 meters, right? And then delta is equal to 0.18 meters. Again, a summary. When I applied P, when I apply this load P, this rigid bar C is going to sink down, right? And what is this displacement equal to? Again, is equal to the gap plus the change in length of B. Okay? So hopefully that is understood. Okay, perfect. So I think that's enough for givens. We move on to unknowns, and more specifically what we're trying to find. What the question wants us to find is the axial strain in rod A. So if you find the axial strain in rod A here, since their bases are symmetrical and they're equal, it's going to be the same for both rods. So we can just find it on one side, and then that will be enough, right? So the strain in rod A, and just as a formula, we're just going to write that the strain in rod A is equal to the change in length of rod A divided by the original length of rod A. Immediately, you understand that we have the original length of rod A. We have to find the change in length of rod A. Okay? We could explain like what we're about to do on this diagram, but again, it's always good to draw it yourself, so that's what we're going to do very quickly, hopefully. So, diagram. This is your rod C. This is your rod A. Your rod B is about here. And then your other rod A is kind of like that. 3 by 3, so kind of like that. Okay, let's put in the dimensions. So this angle right here, 60 degrees. This angle right here, 60 degrees. This length, 2 meters. This length, 3 meters. This length, also 3 meters, right? We are given our force P applies right here. And I think that is all. We can also say that this gap right here is, as we said, this is delta, our variable delta. So this gap right here is delta. Perfect stuff. I think that is all. And we can also say that this is rod A, this is rod A, this is rod C, and this is rod B. Okay? Perfect stuff. Okay. So, what do we want to do now? Again, we want to find the change in length of bar A. To do this, we want to understand where this point goes, right? Because this is the point that is going to cause the movement, right? Because when I apply this force P, this bar C is going to move down. And it's going to move down perfectly horizontal. So basically, what bar A is going to do, it's going to move down with it. So it's kind of going to look like that, right? I want to find the change in length of bar A. If I sketch bar A just on the side here, and I just take, maybe let's just take this part right here. If I just take this bar, and we can draw like the original place, pretend this was bar C, right? And then let's say after some displacement, after we apply load P, bar C is down here, right? So this is, we'll call this point right here F. This is F, and this is F prime, right? So after I apply this load P, bar C is going to go down to its new position, taking bar A with it, right? So this is kind of what the new bar A looks like. I want you to realize that the displacement of this point F is perfectly vertical, right? So if I were to draw a vector saying what the displacement of bar A is or point F is, it would just purely be vertical, right? So this is, we can say delta LA in the y direction, right? It's purely vertical. Let's use a different color, actually. It's purely vertical. right? Is this the delta we're looking for? Well, no, we want to find the change in length. This isn't the change in length. Like the new bar looks like this. This is just the y component of the change in length. The actual change in length we're looking for is kind of this component vector right here. Right? This is the change in length along the axis of bar A. And then it goes to 0 kind of like that. And you can call this the x component. So what we're looking for is this one right here, right? How can we find the change in length of bar A from this setup we have right here? Well, do I know what delta AY is? I hope you do, because we spent, I think I said it like 4 times. I repeated it like a billion times. What is the delta, the change of bar A in the y direction, or the change in displacement of bar A in the y direction, is simply the displacement of bar C. And what did we say the displacement of bar C is? Well, we just said it is the gap plus the displacement of the length of, or the change in length of bar B, right? So it's just this number plus the gap, right? Okay, so we can write that down. We can say that the displacement of point F, or the change, or the displacement of point F, or the displacement of bar C, or in other words, the y component of the change in length of bar A. So all these 3 things are equal. So the change in length, or the y component of the change in length of bar A, is equal to the displacement of point C, is equal to the displacement, or of bar C, is equal to the displacement of point F, right? So I'm going to stick to one of them from now on, and I'm only going to call it, let's pick one. Let's pick this one, because I think it makes the most sense. So the change in the y component of the change in length of bar A, okay? So remember, they're all equal. So if this confuses you, just think of it as the other way. The displacement of the entire bar, or the displacement of point F. I think that's the easiest way to think about it. But okay, so the y component of the change in length of bar A is equal to, as we said, the change in length, or the displacement of bar C, or the displacement of point F, right? Of point F. And this is equal to, as we said before, it's equal to simply the gap plus the change in length of bar B, caused by the force P, which we calculated before. And I should have said this in the beginning, but this is the absolute value, right? Because we have a negative here, so we're taking the absolute value of both of these values. Okay, so what this ends up equaling, the y component of the change in length of bar A is equal to 0. We have to convert to millimeter. We have to convert to meters, because it's 0.18 millimeters. We have to convert to meters. How do we do that? 0.18 times 10 to the power of -3 meters plus 0.005 meters. So we get the y component, right? The y component of the change in length of bar A is equal to 0.00518 meters. Okay, what the heck does this mean? We go back to our diagram, or our third diagram now. So we know the value of this. What are we after? Is this what we're going to plug into our strain equation? Well, no. We're looking for the axial strain. So we need the axial change in length, not the y component, right? We're not looking for the displacement, right? We're looking for the axial change in length, right? How do we find this? Well, good old trigonometry comes to your rescue. This is 60, right? Well, technically, you can also, like, I think, remember the problem with, like, the box, and then you assume that this angle is the same as, okay, actually, this is much easier. So this is 60 degrees, but you can also find this, is what I'm trying to say, just by looking at it. This is 60 degrees, this is 90, this is 30, right? Because this is a straight line. The straight line is equal to 180 degrees. If you subtract 60 and you subtract 90, you are left with 30. So we know this angle right here. This angle right here is equal to 30 degrees. Can I find this vector right here that I'm looking for, the axial change in length of bar A? Well, yes, I can. How do I do that? Well, simply from, I think you use cosine, right? So from cosine, you can say that the actual change in length of bar A is equal to the y component cosine of 30. Right? And another thing, this is, if you were to look at it, it would be 60. So cosine of 30 and sine of 60 are the exact same thing. So either way, you get it right. If you do this lovely calculation with this value, you're going to end up getting that the change in length, the axial change in length of bar A is equal to 0.004486 meters. Perfect. And now you're done. You've done the hard part. You've done the very hard part for some of you, yeah? So you've basically done the question. Now it's just plug and chug. You have the original length. You found the change in length. You found the actual change in length. And now you can find the axial strain by just plugging it into this formula. We should have, to make it easier to digest, we should have called this 4, and we can say deformation. Deformation of bar A. So deformation of bar A. Right? And now, finally, down here, we can say 5, strain of bar A, or axial strain of bar A. Right? Using the equation, the axial strain is equal to the change in length of bar A divided by the original length. You get the axial strain of bar A is equal to 0.004486 meters divided by 3 meters, right? I think that's correct, yep. And what you're going to end up getting as a final value is 0.001495 meters. Let me make this neater. 953 meters per meters.